Hello everyone. So glad to have you watch this video about edge computing on AWS Cloud. In recent years, billions of mobile devices are connected to the internet, generating hundreds of millions of data bytes at the edge of the network. To deal with the data quickly, edge computing is a promising technology that allows the processing of client data as close to the originating source as possible. In this session, I will discuss how AWS considers edge computing on its services. Before we go into the detail, let me give you a quick introduction of myself. I have more than 20 years of IT experience with an emphasis on digital, data analytics, and new technologies. I have worked in a variety of areas, including financial service, healthcare, and technologies. I'm an outspoken supporter of cloud computing. I got certified on AWS Solution Architect Professional, AWS DevOps Engineer Professional, AWS Specialty of Database, Data Analytics, Machine Learning, Security, and Advanced Network, as well as a Microsoft Azure Solution Architect Expert, Azure DevOps Expert, Azure Security Engineer, and Azure AI Engineer. Since 2021, I have also been accepted as an AWS Partner Network Ambassador. By scanning the QR code in the lower right corner, you can connect me on LinkedIn. For a long time, the monitoring and maintenance of public and corporate facilities consume a lot of manpower and material costs. There is also a strong demand for real-time and intelligent processing of massive data in the digital transformation of industries such as power and manufacturing. If the Internet of Things is constructed in a conventional mode, with the rapid increase of equipment, the magnitude of data generated on the edge of network will be very huge. If this data are handled by the cloud management platform, many problems will arise. For example, the real network traffic pressure is huge, the low latency of some devices, real-time collaborative work is difficult to guarantee, and the data security risk of special information increases. To overcome the problem mentioned above, the concept of edge computing is proposed. Edge computing is a distributed computing framework that brings enterprise applications closer to where data is created and where actions are taken. Cloud computing and edge computing are usually used for comparison, and edge computing is actually born out of cloud computing. Then, since there is cloud computing, why do we need edge computing? Cloud computing can process a large amount of information and can store short and long-term data, which is very similar to our brain, which stores information because of the gray matter layer. However, the spinal cord also contains the gray matter layer, and this feature helps the spinal cord deal with the simple information quickly. Edge computing to cloud computing is like the spinal cord to brain. Edge computing has a fast response speed and does not require cloud computing support, but it is low in intelligence and cannot adapt to the processing of complex information. Everyone has been injured. The risk avoidance action is before consciousness is generated, and it is very fast, avoiding your body harm. If we left the brain handle the decision to avoid burns and produce actions, it will take much more time for the body to react. In cloud computing, data is collected, processed, and analyzed in a centralized location. On the other hand, edge computing is based on distributed computing environment, We can summarize some general difference based on the features of edge computing. First, edge computing uses small computing power units to meet data localized high-speed transmission and real-time processing. Therefore, edge computing has limited compute power, memory, and storage capacity compared to cloud computing. Secondly, data filtering and analysis are implemented at edge nodes, so the computation efficiency is higher for edge computing. Since the edge devices can be deployed to many cases, edge computing is more complex than cloud computing. Although edge computing has those attractive features, the existing edge computing technology is not enough to support the complex and huge data processing scenario being deployed on the edge side. Therefore, companies can keep their IoT devices running fast and efficient without compromising critical analytical data that might help them enhance services and drive innovation by combining the data gathering capability of edge computing with the storage capacity and processing power of the cloud. As the most comprehensive and widely used cloud platform in the world, AWS addresses the needs of edge computing by developing an integrated set of edge-to-cloud services and solutions that combine global cloud infrastructure to provide data processing and analytics capabilities as close to where the data is located as possible. Internet of Things and 5G are the most common applications for edge computing, and AWS has a well-established offering in both areas. In the aspect of IoT, AWS launches IoT Greenglass with IoT Core in the cloud to quickly analyze the data generated by IoT sensors and devices, while in the aspect of 5G, AWS constructs the infrastructure of AWS wavelengths to deliver ultra-low latency applications for 5G devices. Next, I would like to move on to the details about IoT. To make you better understand what the IoT is, here I give some explanation. According to Wikipedia, the Internet of Things, or we call it IoT for short, describes physical objects that are embedded with sensors, processing ability, software, and other technologies that connect and change data with other devices and systems over the internet or other communication networks. In other words, IoT refers to any physical device system that can receive and transmit data over a wireless network with limited manual intervention. All of this are possible because of the integration of computation devices in various objects. Here is a comprehensive example of IoT. The smart thermostat can receive location data from your smart car when commuting. These networked devices can adjust the temperature of your room before you get home without wasting too much electricity. Compared with manually adjusting the thermostat, it does not require any intervention from you and can achieve a more ideal effect. To predict the best time to adjust the thermostat before you arrive home, the IoT system may connect to the internet to obtain data about the real-time traffic pattern in your area, as well as the long-term data collected by your connected vehicle to obtain your commuting habits. In addition, in order to perform larger-scale optimization, the utility company will also analyze the IoT data collected from various smart thermostat customers. These data are continuously sent, received, and analyzed in the feedback loop and finally wake up the smart thermostat at an appropriate time. This is a traditional IoT architecture based on AWS IoT Core, which is a cloud service. IoT devices obtain the data from users and transfer this data to the cloud. Then the features of analytics or artificial intelligence can be accomplished in AWS IoT Core. However, it is actually hard to meet the practical needs. In addition to the problem of big data transmission, as described before, the storage and the computation power of the cloud platform does not work in a timely and effective manner, and many times IoT devices do not maintain a stable connection with the cloud all the time. Greenglass bridges the middle segment between AWS cloud and IoT devices, mainly dealing with the edge computing part. It is able to continue to run when AWS cloud service interrupts and even continue to execute Lambda applications on the edge devices. With Greenglass, developers are syncing some of their real-time processing and response capabilities to edge computing devices. Greenglass is essentially a software that runs local computing, messaging, data caching, synchronization, and ML inference functions on connected devices in a secure manner. With AWS IoT Greenglass, connected devices can run AWS Lambda functions, synchronize device data, and communicate securely with other devices without even having to connect it to the internet. The workflow for AWS IoT Greenglass is summarized in this flowchart. The user uploads the training model to Amazon S3 at the beginning and then generates a training model by selecting one of Amazon SageMaker's existing algorithms. The model is copied to another Amazon S3 in the form of a compressed zip file. The training model is then copied to the AWS IoT Greenglass on the edge side and deployed to the appliance, giving the appliance itself the ability to infer quickly, thereby reducing latency and allowing the appliance to respond quickly. To give you a better visualization of what AWS IoT Greenglass can do and where it can be placed in real cases, the case study of predictive maintenance of connected mobility can be looked at. Applying machine learning to vehicle and fleet data can predict maintenance needs. This helps reduce unexpected warranty costs, improve fleet uptime, and optimize costs, including maintenance, tires, and fuel consumption. So how does this machine learning model manage to warn of failure before they occur? Firstly, we need to collect the data at the device side while the device is operating normally. The vehicle works locally with the data it generates before securely transmitting the same it requires to the cloud by AWS IoT Greenglass. Then data from the vehicle is filtered and processed on the fly based on defined rules by AWS IoT Core before being saved in Amazon S3 for future study. After that, to detect proper equipment problems, machine learning models are swiftly built and deployed. Meanwhile, additional purpose-built data stores in the data lake. After training the ML models and obtain the prediction, alters are sent to fleet managers and drivers when an anomaly is detected from the ML model through Amazon SNS. Finally, the driver is able to arrange maintenance before an equipment failure occurs. As we can note from the above example, the AWS IoT Greenglass appliance can manipulate the data it generates locally, so it can respond quickly to local events while still using the cloud for management, analysis, and persistent storage. This edge plus cloud architecture is very important for the IoT. In addition to this, the emergence of 5G has led to the rapid development of the IoT scene. AWS also provides good service in this infrastructure of 5G. AWS Wavelengths is meant to allow applications that require ultra-low latency for 5G devices. By extending AWS infrastructure, services, APIs, and tools to 5G networks, AWS Wavelengths integrates storage and compute into telecoms carriers' 5G networks, allowing developers to build innovative 5G end-user apps that require single-digit millisecond latency, such as IoT devices, game streaming, autonomous vehicle, and live media creation. The location of users, the location of the regions, and the paths taken to reach the application in the region all impact the latency of application deployed to AWS regions. When looking at a big group of mobile users, the delay is frequently in the tens of milliseconds range. When compute instances are running on a site that is part of the mobile network, the network distance is reduced. Latency is predictable and has less jitter on mobile networks since the network channel is shorter and the quality of service is strictly maintained, which is advantageous for applications like live streaming and other that require exact synchronization between users. In addition, use cases requiring a higher quantity of data transfer can be processed sooner in the data network path, reducing the amount of bandwidth used in the backhaul networks. The capabilities of AWS Wavelengths can be expanded to suit a variety of scenarios. AWS Wavelengths, for example, offers the ultra-low latency required for live streaming high-resolution video and high-fidelity audio, as well as embedding interactive activities to live video feeds. Real-time video analytics allow us to generate real-time information that help improve the live event experience. Real-time game streaming, on the other hand, relies on low latency to maintain the user experience. Wavelengths allows us to stream the most demanding games from wavelength zones to end devices with limited processing capacity. In the sphere of industry, industrial automation apps employ machine learning at the edge to analyze photos and videos in order to detect quality concern on fast-moving assembly lines and to initiate corrective measures. These applications may be deployed without the need for expensive GPU-based servers on the factory floor, thanks to wavelengths. In the field of healthcare, machine learning-powered video analytics and picture matching tools help doctors diagnose problems more quickly, such as polypus recognition. In a wavelength zone, picture or video feeds from medical devices are analyzed and the result is sent to the surgeon's medical device. With the gradual maturity of 5G technology, we believe that in the future, network latency can become shorter and shorter, and with the help of 5G, the edge computing will be used in a wider range of scenarios. You may find all reference materials illustrated in this video from here. The world is becoming more linked than ever, with billions of gadgets producing tremendous amount of data that is pushed to the cloud, enabling new intelligent, responsive applications. Reduced latency, great security, and more bandwidth at the edge are becoming increasingly important for these applications. It is truly possible to have a cloud without boundaries using AWS Edge technologies. Thank you so much for watching this video. Hope you enjoyed learning.